Welcome to the Introduction to Amazon SageMaker webinar. Thanks for joining us today. What we'll do today is walk through what Amazon SageMaker is at a high level. This is actually the second of the Introduction to Amazon SageMaker webinars. The first one will provide more detail on background and context around why we created SageMaker. This one is actually going to focus more on the second area, which is how do we get started with using Amazon SageMaker. So we'll walk through two demos. The first demo will be how to build your own recommender system with MXNet and GlueOp, and the second demo will go through bringing your own algorithm with R. And then we'll walk through an example use case from one of SageMaker's customers and finish with some Q&A. So starting with what is SageMaker? SageMaker is a managed service that provides the quickest and easiest way for machine learning scientists and developers to get their models from idea into production. SageMaker has three components: UX, training, and hosting. And each of these three components can be used independently or all together, which is how we think they work best. And on top of these three main components, we've added several layers, such as Amazon's fast and scalable algorithms, which are custom implementations that Amazon has built for common machine learning algorithms, idiomatic and distributed support for TensorFlow and MXNet, and the ability to bring your own algorithm. We also have a service called hyperparameter optimization in preview. Hyperparameter optimization is a new technique which seeks to explore the hyperparameter space of a machine learning model to provide optimal fits in an automated way. So digging more into the user experience component, SageMaker includes a notebook instance feature, which allows you to very quickly and easily spin up your own instance that's running a Jupyter Notebook server. But it's not the only way that you can use to access SageMaker's other two components. We have a SageMaker Spark SDK, which allows you to use Spark EMR and run SageMaker's custom estimators and transformers right from your Spark workflow. In addition, we provide a console, which provides a point-and-click user experience. And we can also you can also use SageMaker from your own EC2 node or from your laptop. The second component of Amazon SageMaker that we'll walk through is training. One of the great features of SageMaker training is that it's zero setup. When you create a SageMaker training job, we spin the instances up for you. We load the algorithm container code. We load the data sets. We process the algorithm code, wrap up the outputs, send them back to S3, and tear down the cluster, all without you having to change any of that functionality or code any of that functionality up yourself. We also support streaming data sets and distributed computation. The algorithms themselves live in Docker containers, so technology you're used to, and those are stored in a repository of the Elastic Container Service, which is AWS's tool for containers. Finally, once you train the model, you can deploy to a variety of different sources. You can deploy with SageMaker hosting, or you could deploy locally. The model artifacts are yours, so you can take them and put them where you need, including deploying them in IoT devices like Greengrass or AWS's DeepLens. The ability to train a deep learning model in Amazon SageMaker and then deploy that to a DeepLens to do inference at the edge is a really powerful aspect. The third component of Amazon SageMaker is hosting. And here again, the goal here is ease, so one-step deployment. Once you've trained your model, it's very quick and easy to deploy a real-time online predictor. These endpoints are going to be low latency, high throughput, and highly reliable. You can also deploy multiple models behind the same endpoint for A/B testing, and you can bring your own model. So if you've trained your model outside of SageMaker, that's okay. You can still host it within SageMaker's endpoints. The first layer that we'll talk about is Amazon's own fast and scalable algorithms. So we've built several SageMaker algorithms ourselves, and we have our own implementation of XGBoost. We also coded up factorization machines, linear regression and classification, and forecasting for supervised learning use cases. We have K-means, PCA, and word2vec. These are common algorithms in either the preprocessing or clustering space. And then we have several other algorithms like image classification, which uses convolutional neural networks to classify images. And we have latent racial allocation and neural topic modeling to comb through large corpuses of text and pick out relevant topics, as well as a sequence-to-sequence algorithm, which is good for neural machine translation, so translating from one language to another. The second layer that we'll talk through is idiomatic distributed TensorFlow and MXNet support. We've pre-built TensorFlow and MXNet containers in SageMaker so that all you have to do is write your code as if you would naturally, and then submit that code to the pre-built TensorFlow and MXNet container so that it can run in SageMaker's distributed training environment. So the workflow that we kind of find most data scientists wanting to use is taking a sample of the data, exploring and refining models in a single notebook instance, and then using that same code to train on the full data set in a cluster of GPU instances, and then finally deploying into production. And the way these TensorFlow and MXNet containers enable that is really a powerful experience. So the third Amazon SageMaker component that we'll talk through is bringing your own algorithm. When bringing your own algorithm to Amazon SageMaker, you get to pick your preferred framework, whether that be scikit-learn, R, PyTorch, Java, anything that you can bundle up into a Docker container. You add the algorithm code to the Docker container, and how to do this is documented on the SageMaker AWS documentation page. And then you send it to a repository of Amazon's ECS, Elastic Container Service. The final layer that we'll talk about is hyperparameter optimization. As we mentioned earlier, hyperparameter optimization is all about tweaking the levers on your machine learning algorithm to find an optimal fit. And so what our hyperparameter optimization service does is run a large set of training jobs with varying parameters in an interactive way to search the hyperparameter space for improved accuracy in your model. And by doing this and exploring and exploiting different parts of the hyperparameter space, you can really get an optimal fit. And as we mentioned earlier, this service is in preview currently. So now we'll move on to how I get started using Amazon SageMaker. We'll walk through a couple of demos now. So the first demo that we're going to walk through is using neural networks and embeddings for recommendations. As you can see, I've loaded up the SageMaker page in the AWS console, and we'll move to our notebook instances. I've spun up a special notebook instance with a P2 MLP2 X large instance type, and we will open that up. We can see the familiar Jupyter dashboard page that's running from our Jupyter Notebook server on our notebook instance. For this use case, I'm going to go into the Gluon recommender system folder that I've created, and I will open up a Python notebook that I have set up for that. And I'm going to run all of these cells. And then switch over to a predefined, a pre-run version of that same notebook. So implementing a recommender system with SageMaker, MXNet, and Gluon. We'll talk high level about the background of recommender systems. Then we'll go into setting up your notebook instance, bringing in data, exploring, cleaning, and preparing it for your modeling, training locally within the notebook instance itself, moving that training over to SageMaker, and finally hosting within SageMaker's hosted endpoints. Recommender systems were one of the early catalysts for machine learning's current popularity, whether it was Amazon customers who bought this also bought that, or Netflix's $1 million movie recommendation challenge. They're typically holistic system, actually, with a lot of different interrelated components, but we're going to limit ourselves today to just the core component, which is typically user item rating prediction. Matrix factorization has been particularly successful at generating these types of predictions, and now that we have these great deep learning frameworks, they really allow us to introduce nonlinearities and add enhanced performance. So we're going to start with a data set that has Amazon Digital Review data, and we're going to explore the notebook instance first and then showcase how we would train that in SageMaker's training environment. So the first step is setting up, and we're going to just define an S3 bucket where our data is going to live, and an IAM role that has permissions to access that data and use SageMaker's training and hosting functionality. We're going to import our libraries that we'll need from Python. MXNet, Pandas, NumPy, these will be familiar to Python data scientists. Now we'll bring in some data. So we're going to grab our data set from a public data set that's in S3, and we're going to drop it into the temp space within our notebook instance. It's about a half a gigabyte of data, and so we don't need it to stay around for very long, so we'll drop it in that temp folder, and then we're going to read it into a Pandas data frame. And as you can see from the data, we have customer ID, product ID information, what that product title was, how many ratings that user gave that product, and even the textual aspects of the rating and review. For our use case in particular, we're really just going to focus on customer ID, product ID, and star rating. So I'll limit my data frame down to those fields, and then I'm going to also try and get rid of some of the long tail. Most users haven't seen most movies, and most movies haven't been rated by most users, and so we're going to try and trim out customers who may have only rated one thing, or movies that may only have one item, one rating, because we probably wouldn't recommend those anyway. So we have some quantiles here of our data set, and we can see that only about 5% of our customers have rated five or more ratings, and only about 25% of our movies have 9 or more customers who've rated them. So we will clean those out, and we'll also add a sequential index. The customer ID and product ID that you see are Amazon's own internal generated. What we want is a nice sequential index for each user and item. So that's just part of the data preparation and cleaning phase. Moving on, we're going to split our data set into test and training. Testing is going to be a data set that we use to judge the accuracy of our model on data that it has not seen and the model wasn't trained on. And so we're just going to grab the last review for each customer ID and split our data frame, split out into 2 data frames. Now that we have our test and train data, we're going to start getting our data prepared for use in MXNet. So we'll go from our Pandas data frames that we have into MXNet ND arrays, move that into this sparse matrix dataset class that we've created here that handles that sparsity and long tail well, and then moves it into data iterators, which can be used by MXNet's model training. So once we've done that and created a train iter and a test iter, we're going to move into training locally. So now that we've trained locally, we're going to start by defining our network. And our network is going to be a custom matrix factorization block. And the main components to look at here is the glue-on neural network embeddings that we're going to create for users and items. We have a dropout layer and then a dense layer, which has ReLU activation. That adds a little bit of nonlinearity. And then really all we're doing here is multiplying those 2 matrices together to generate our predictions. So we'll create a net that is of that matrix factorization block, and we'll use a 64-dimensional embedding. These embeddings, what they do is they take very large data sets. We have a large number of users and a large number of reviews, and represent them as a much smaller, lower dimensional representation of that data that still preserves a lot of the characteristics of the original data set. Now we'll set the parameters for our neural network. We're going to start by initializing those parameters, and then also our optimization parameters as well. These can be tweaked and tuned with hyperparameter tuning for better performance. For now, we'll just leave them as they're set. Now we define an execute function. This function trains our neural network. It loops through a number of epochs, brings in our data, and then uses the autograd functionality in MXNet Glue-On to train the model. The next step would be creating this evalnet function. This is run actually as part of the execute function, and it's going to test to see how well our model is doing on predictions for the training data set and the test data set. So I'll run that for 5 epochs and output my trained network that I get from that. And as you can see, we have our root mean square error, which is our metric of accuracy, being printed out here. You can see it go down as we do subsequent epochs, and our test accuracy bounces around a little bit, but in general is going down as well. However, that process took us over an hour and a half to run through. So you can imagine, iterating on this on maybe a smaller sample. Maybe it goes faster, but it still is a time-consuming effort. And so what we'd really ideally like to do is run in the background to improve our productivity, especially if we're going to scale up to an even larger data set. So let's go into what training with SageMaker would look like. For training with SageMaker, the most important part is that we wrap our code up that we prepared in those first 15 cells that we just walked through into a single .py script. And I'll walk through what that looks like. So we've created this single .py script. And if we look at that Python script, we can see what it does is it wraps up the previous functions that we ran in the first 15 cells of the notebook. We'll start here and go to this prepare training data function. And this is really the first 5 or 10 cells of the notebook that we've just wrapped up into a function where we're reading the data into pandas, and we are filtering out customers and products that we don't want, and then converting them to MXNet data iterators. We've taken the sparse matrix dataset class and the valnet and execute functions and the MF block class and just copied and pasted them in as they are. And then all we've done is add one extra function here called deftrain, which gets our data from this, and this is documented how we do this, gets hyperparameters for us, sets up our context and key value store, which are necessary for training in MXNet, and then the same exact way I defined my net and executed the training on it as I did in the example notebook. And I returned that train net class, and I've built one extra small little function that saves that information out so that I can later use it for hosting. So now that I have that, I can go and test that code locally by just importing it as if it were another library and running that. Since it took an hour and a half, we won't do that. We'll move on to the actual data aspects. So in order to train with SageMaker, we need to have our data sitting in S3. So we're going to take that original S3 data set that we grabbed from the public bucket and move it to our own personal bucket so that we can run the SageMaker training algorithm on it. Now that I've got my data set up, I'll start training with MXNet. And to do that, I will use the SageMaker Python SDK, which has a custom MXNet estimator built into it. So what I do is I pass that recommender.py source script that I just walked through. I define my IAM role, which defines permissions. I walk through my hardware setup, training instances, the number and type. For this, I'll just use another P2 and one of them, but I could easily set that to multiple P2s, and I could easily set that to a larger instance, like a 16x large. I'll pass in hyperparameters, just like we set above, and I'll use .fit, just like you would in scikit. Only this time, I'll, instead of specifying a local data frame or a local NumPy matrix, I'm going to specify a S3 location that I sent my data to. And as you can see, all the CloudWatch logs will come immediately cascading into the notebook, and you can begin to track your training job. And over time, we'll track each of the epochs, and we've got a lot of information here, which we controlled with our MXNet logging, so that we can help troubleshoot our process if need be. But at the end, the most important part is we see job complete, and on our last epoch, we have improved training and test error. So now that we've trained our model, we can go ahead and deploy it. And this will take a few minutes to go set up those instances, but it's really just a couple of lines of code to define that we want one instance up, and we want it to be an M4X large. So this is another nice aspect, is we can train on a GPU instance and then very easily deploy to a CPU instance. Once we have that up, we can generate predictions in real time from our endpoint. So with predictor.predict, we're going to find the first user and items 1, 2, and 100 and estimate what their star rating would be for those products. Now evaluating our neural network. we can see here that we'll generate a naive baseline of how good our model should be. And what I'm going to do is just take the average rating within our training data set and estimate that for our test data set. And you can see a root mean square of 1.26. If we compare that back to the error we had on our test data set in the neural network model, you can see we've substantially reduced our root mean squared error. And with additional hyperparameter tuning and tweaks to the data, I'm sure we could get even better than that. So let's evaluate it subjectively as well. So what we've done here is we've grabbed a single user, user 6, and we've looked at what their top rated movies are, because the recommendations have to feel relevant to a user. And so evaluating these recommender systems subjectively is as important as objectively. So what we've got here for user 6 is they appear like kind of prestige TV dramas, so Under the Dome, Extant, Rome, True Detective, as well as some sci-fi, Star Trek Into Darkness, and they appear to dislike kind of screwball comedies, Your Highness, Dinner for Schmucks, a couple other things. And so what we're going to do now is take every movie in our catalog, or every video in our catalog, and generate a prediction for what we predict that user would rate the title as, and sort them to see what we would recommend. So you can see we recommend some well-reviewed TV dramas like Mozart in the Jungle, Hell on Wheels, 6 Feet Under, as well as some sci-fi, things like I Am Number 4, Interstellar, etc. And then the things that we wouldn't recommend are, again, goofy comedies, Out of Towners, Liar Liar, and a few others, right? So we can see that, intuitively, it seems to make sense, the predictions that we're generating. So just to wrap up what we did here, we generated a user item prediction model very quickly, very easily. We showed the kind of workflow that naturally exists within SageMaker. We could obviously improve this with hyperparameter tuning or tweaking our data in different ways. But for now, we've got at least a proof of concept that we can start working with. To wrap up, all we'll do is make sure that we delete our endpoint. As those stay live, we don't automatically remove those for you. So to save cost, we'll remove those. Now we'll begin with our second demo. And this demo is available in the sample notebooks repository. These examples are all available on GitHub as well. So please do go look through. There's a lot of material here that can show you how to get started and get using Amazon SageMaker for your specific use case. In this case, we're going to talk about bringing your own algorithm, and we'll use R to do that. So I'll open up the example notebook here. And again, we'll move through this pretty quickly since we've already seen it once. But the portion I wanted to focus most on is not the preparation, but the code that you'll need to set up in order to bring your own algorithm. And here we can see that it's actually 3 simple files. The first will be a Docker file, and that Docker file has information. It starts from an Ubuntu Docker image, and all we have to do is set it up to apt-get and install a few packages. So rbase, rbase dev, and then we run an R command to install the packages that we'll need for our algorithm. So in this case, Plumber is going to help us with the API serving, and MDA has an algorithm called Multivariate Adaptive Regression Splines, or MARS, that we think really sort of represents the beauty of R, which is that there are so many great packages available in R's repository that fill very unique use cases that people like to use. And so we're going to install both those packages, and then once we've done that, we copy over the 2 other code files, this mars.r and plumber.r file that we've written ourselves, and we set our entry point up to run mars.r from the beginning. So with mars.r, you can see it looks just like natural R. We bring in our libraries at the top. We specify some information up here about paths that we're going to need. This is all documented as to where data will flow on the Docker container on the SageMaker training instances. And then we create 2 functions. The first is a training function, and the second is a serving function. And logic down here will tell the container which one to run, whether you're doing training in SageMaker or whether you're doing SageMaker hosting, then it'll run serve. So that train function is, again, pretty simple and pretty natural R. We bring in our data, we convert the data, we do some light data manipulation using things like model matrix and lapply, and then we run a multivariate adaptive regression splines model, and we just save that out as a Mars model.r data, so a very natural format and very easy to do. Our serve function brings in plumber.r, and we'll walk into that next. So plumber.r is another fairly short script. It has two main components. There's a ping, which returns a empty response body to a ping get, HTTP get, and that just tells SageMaker that our process is still alive and running. And then there is post. It has to take a post on the invocations channel, and the request there is going to include a body which contains the data. So when I'm trying to make a request from a SageMaker endpoint, I do an HTTP post command, and I submit a request with a body that has data, and this just parses out that data. It expects it in a CSV with new line commands separating the different rows, runs a model matrix on it, does a little light processing, and then just uses R's own predict function based on that Mars model build. Right? And then real quickly, we'll talk through the alternative approach to how these are executed, right? So once you've set up your three files, you need to go and publish that information to a Docker container in ECS. And so we've got a little shell script here that runs right from within the notebook and publishes your Docker container to ECS so that it's ready for SageMaker to consume. So very easy, doesn't need many edits. The next thing that we'll do is we'll take our data set. In this case, we're just going to use Iris, and we're going to send that to S3 as well so that SageMaker training can pick it up. Now for training, we're going to use the alternative format for SageMaker information, for SageMaker creating training jobs. So we have this JSON blob here that specifies all the parameters, and we can specify the role, the training image, the hardware types, input data and output data, and then hyperparameters, all in one big JSON blob. And then we just run create training job. And this could be done from within Python. This could be done using that SageMaker Python SDK that we showed in the last example to kind of clean it up and make it simpler. Or it could be done from the command line. And that's one of the reasons that I kind of wanted to show both of the different ways of interacting with SageMaker, is this more AWS SDK JSON blob way, as well as the SageMaker Python SDK. So we'll create the training job and we'll pass in those training parameters that we just created. And that will spin up a separate training instance, run the job, and dump the results down to S3. Now, once we have the results in S3, we can begin hosting our model. And this takes 3 steps using the AWS SDK. We first create a model. So we register our model artifact for hosting. We then create an endpoint configuration. We tell what kind of hardware we want to use. And we go ahead and create our endpoint by passing in that endpoint configuration. There again, takes a little bit of time to spin up those instances, but once they're ready, we can do live inference on them. And so we have a runtime here. We invoke our endpoint. We pass in a payload. In this case, that's just the CSV data that we originally used for training. And we output our predictions. And as you can see here, we're trying to predict sepal length in the Iris dataset, and we do a pretty good job as our predictions are lining up well with our actuals. Heading back to our slides, we're going to talk through Intuit's near real-time fraud detection use case using Amazon SageMaker. So Intuit is the maker of products like TurboTax, QuickBooks, ProConnect, and Mint. Very well known in the financial business. Lots of financial transactions go through their software at some point in time in their life. Intuit uses artificial intelligence and machine learning in lots of their products, from everything from providing smart recommendations to customer care and expert advice. The use case we'll talk about today is fraud detection and prevention. So they have a Kafka data stream of information that flows in. They then pre-process that information in Apache Spark and Amazon EMR. So they do all their feature generation and calculation within Spark. They pass that to a feature store where Amazon SageMaker's model training is able to pick it up, train a machine learning model, and then that model is then picked up by Amazon SageMaker's hosting, which also references a lookup that gets created from data coming out of Spark EMR. And then that links to a client-facing service, which provides real-time fraud estimation within this pipeline. Thank you for attending this Introduction to Amazon SageMaker webinar.